we're at 3V Performance. I'm Tom Vigue, I'm the owner here. And the guys from Tech came down, brought us some components. They wanted to do some valvetrain testing, some durability stuff, peek at their cam low profiles, and kind of get an idea what Spintronic testing is all about, where the limits are with some of their stuff. But mostly just durability at this point.
So what are we doing?
Testing some new valve spring retainers this morning.
So how are we going to test it?
So we've got a Spintronic hooked up here. We've got a mock-up block. And so we're going to slap it back together with one of our most popular cams and spin it some RPM, see what it does.
So what do we have?
So we've got some stock 243s that we threw together just for the test. We're running a PAC 1208X spring on them just to add a little load to test durability on the new design. We've got a new design of steel and titanium. Our main priority today is testing the titanium because it will be available first. Because we need to do a little more groundwork with the steel, but we're gonna test them both today.
And so this one is steel.
So this is the steel retainer. This is the titanium. Physically, you can't really see a difference currently with the state that they're in. No laser etching or anything. So what really puts it to the test is kind of sort of simulating a street drive and simulating drag racing, which you can do with a Spintron. You can simulate RPM up and down, gear shifts, anything of that nature, anything that the engine would normally see, it can simulate. But we're gonna test RPM, test max RPM of the camshaft for one thing, the camshaft that we're using, and then we're gonna test durability on these things with RPM and with cycles, basically. Now, Spintron is basically just an electric motor in all reality. You can interface different engine types to this adapter and simulate lots of valve events and lots of different valve testing, or valve spring, valve train testing that goes on with them.
Oh, this is a standard LS foundation, hydraulic roller, standard LS valve train, minus tech spring and retainer package, camshaft package. So it's your basic cathedral port LS foundation.
And then tell me, there's two big holes in the side of the block, right?
Yep. The way we monitor valve control is we machine a big hole in the cylinder. We've got a laser over there that sticks up inside here, and it looks up at the bottom of the valve itself. And in the block, there are no rods or pistons or nothing. There's just a large shaft that sits in the main saddle that drives the timing chain, which drives the camshaft, and that's how the valve train works, just as normal. It uses a standalone dry sump system, which lubricates all the bearings and oiling system like factory. So we can control oil from this, and then we control the engine speed through a large 75 horsepower electric motor. That's what spins the engine at whatever RPM we tell it to spin at. So we can do single engine speed testing, steady state, 1,000, 1,200, 3,000 RPM for as long as we want. We can do sweep testing like you're accelerating the engine. We can do a sweep like you're accelerating and shifting going down the racetrack. We try to simulate as close to actual running conditions as we can with this type of device. This is the configuration and how we run the engine at what engine speed. And right now it's all controlled manually. So I'm just going to try to bring this thing up to whatever Matt wants for a baseline, and then slowly bring it up 500 RPM at a time. And the camera is just going to keep recording the actual valve motion. It'll take snapshots of it. I know mostly right now the game was just to get cycles on it and then just look at the components when you take it apart. So we'll kind of see where the camshaft falls off, where it starts to give us a little bit of issues. Maybe we'll hang it around there a little bit, kind of beat up on this stuff a little bit, and then it'll give you something to look at. You know? We're not seeing any issues with valve bounce that I'm concerned about. 7 thousandths is pretty much the general rule of thumb we always went by in NASCAR. That's the rule of thumb I use. I can't tell you why. It's what we used. It was good enough for them. It's good enough for me. And that's kind of what I've always set my standard at. So once I start getting above 7 to 10, and if it's just a single bounce or if it's a multiple ripple, that's an entirely different problem. But that's kind of what I look at. And we're not really seeing that here. Other than a lot of initial deflection going on here, our closing ramp isn't bad. Like I said, we can go higher. I can go to 75, go to 80. Kind of see where this thing taps out at.
Send it.
Send it. There you go. Fuel it up and send it.
We've learned a lot about the information that you can get out of Spintron testing so far.
What is it telling us? Anything unique about the cam?
Yeah, it's telling us that our shelf cam in a 5.3 at 8,000 RPM may not be the best thing to do.
Why is that?
You get a little bit of instability in the valve train at 8,000 RPM, but I don't know anybody personally with a 5.3 and a shelf polluter cam that can turn 8,000 RPM.
That cam doesn't need to go to 8,000 anyway. So
we're just theory crafting here. We're taking a 7,000 RPM cam and overspinning it to see what happens.
We're trying to do some durability testing on the retainers. So what we learned here today will be when we disassemble.
Yeah.
Mainly.
Some of that standing mile stuff where they get up there in that RPM where it's just struggling to get that last. You have an idea where the fuss point is on this package now.
Yeah, because it's never going to sustain 8,000 for even as long as that was.
Correct.
You know, or it's never even going to sustain 7,000 in most cases.
Normally, I'll set this up where it goes, and it comes back down.
Yeah.
Hanging it like I am, I'm really kind of abusing it, leaning on it. Just trying to make sure that we don't have any hidden issues. That's all.
Yeah.
So that.
Started to fall apart at 75. We didn't go to 8. It's not a cam package you're going to run that high.
Yeah.
So when we look back at this data here at 7,000, I don't see a problem with it. Just know that you're knocking on the door of an issue. So
what did you just do?
changed the intake push rod style from a dual taper to a no taper. So it'd be a single straight 5/16 diameter, same wall thickness, 80 thousandths wall thickness.
So is it ultimately a lighter push rod?
A little bit lighter on the gram scale, but more than anything, it changes the frequency and how that frequency gets transmitted through the other side of the valve train to the actual valve, which is what we're monitoring on the laser. That's what we're going to try to change fuss point. Pretty much just a little bit of a durability test, set it at a particular RPM and just let it run there for, you put cycles on it, and then evaluate the condition of the components after. I haven't had anybody ask me to.
Could you do it if someone asked? Mm-hmm. The way I know who to direct them
we were doing it, but we don't have time to do that kind of thing anymore. $165 degrees. Valve springs 150. Retainers 150. Nothing wrong with that.
Any temperature difference?
Nope.
What about the retainer? You checked it?
Yep, same. No, it's oil temp is all it is. If that was really pissed off, man, that thing would be 200 plus. And it don't take long either.
We're just looking at things while it's still hot, making sure everything's at nice even temperature. That just kind of signifies that there's no bad harmonics or odd wear going on. As long as everything's the same even temperature, that means there's no excess scrubbing or anything. So everything's holding up really well.
What we just finished, about how long, what kind of RPM, what did we just do?
So it was about 4,000 RPM, between 4,000 and 1,500. Mostly at 4,000 RPM for about 30 minutes. We slowed it down to 1,500, did some slow-mo videos of the valves, and took some video. And then we ramped it back up to 4,000 for another 10 minutes or so. Just let everything get nice and hot, just to see if we could wear anything prematurely. Basically, we're simulating highway driving. I know 4,000 is a little excessive, but you know, we have a window of time that isn't the same as a road trip. You know, we've got a few hours to do this, so we just jack the RPM up to simulate more wear.
Because if we set this, we could have set this thing at 7,000, but yeah, lower RPM is a higher load. What's it do with the valvetrain at 4,000?
Yeah, so at 4,000, it's got more load on the retainer itself over that course of time. We have done some sweeps. We've done some simulations of like gear change scenario, 4,000 to 7,000. This isn't the best simulator for a gear change or like a track condition, but we have done some sweeps with it, and then we have done some sustained high RPM, and we've done some stepped RPM, 500 RPM increments going up to about 8,000 just to see how things acted. We're back at the shop today after doing some testing with 3V Performance on some burning valvetrain products. We spent the day down there with those guys testing some new valve spring retainers. Something we've been working on for a couple of months now. We think we've got a pretty exciting design. So what we went down there to do was to do some stress testing. That was the initial reason for going down there. We've got a design that I wasn't comfortable with, trusting a computer simulation for evaluating the stresses on it. So I wanted to see in person and do some kind of extreme testing versus what they're going to be used with. And I think we did that pretty successfully, and we learned a lot of things while we were down there. So what we used is one of our more popular cams, which is our 5.3 liter cam. And we actually used some dual taper push rods, some standard 5/16 080 wall push rods. We went with a set of Morel 5290s. They're more of a budget-oriented lifter. So we used those components in conjunction with just a stock block that he has modified to work with his Spintronic machine. We used a set of 243 heads with factory valves, you know, no fancy port work, no fancy guide work. Springs, we used PAC 1208X springs. And the reason we did that is because I wanted to simulate a little more pressure than our normal kit comes with, to do a little, like I say, a little extra on the testing. Yeah, so we have one head set up with steel retainers and one head set up with the titanium design. That way we could test both materials simultaneously. What we were trying to do was find out, number one, durability. Number two, I wanted to see what kind of instability it may have with the way it's designed. Because what we've done is we've taken a lot of mass out of the retainer itself. It will be the lightest, at this time, it will be the lightest factor or lightest retainer for an LS engine on the market. So we wanted to make sure that it was still stable, and wanted to make sure it would hold up as well. The Spintronic pretty much confirmed everything that we saw on our computer simulation, which was that it would do the job just fine. You know, we're pretty excited about it. We had a cam that was never intended to rev to 8,000, and we
comfortably revved it to 8,000 without an issue. We didn't have any kind of stability issues at 8,000 RPM. And then we also did like an endurance test. So we did 4,000 RPM for about an hour. And then we also did rev cycles. So we did a lot of up and down, like sort of simulating gear change, but a lot of fluctuation of RPM to kind of put them through their paces, got them real hot, let them cool off a little bit.
And why 4,000 RPMs and not 8,000 RPM for an hour?
You put more load at mid to low RPM on the retainer itself, I guess because of the time that the valve actually spins open. Because slower engine speed, it's technically open for a longer amount of actual time because it's spinning slower RPM, so it goes through the cycle slower.
So the retainer is working harder at 4,000 RPM than it is at 8,000.
Yeah.
We tried 2 different push rods to see if that affected valvetrain geometry.
Yeah, we wanted to make sure we didn't have any deflection in most of our stuff. That way we could put as much stress on it as we could.
And so you're pretty happy?
Yep, I'm very excited about this.
Right on. So tell me about it.
All right. So what we've done is we've taken the retainer, your typical design retainer, and we have eliminated some of the mass of the retainer itself. So a lot of times you'll have what looks to be 3 steps on the bottom side of a retainer. And what that 3rd step is a location for the inner spring. And what we've done is we've eliminated that step, and we're locating on the inside of the outer spring at the top. And then we've machined special seats to make up the difference that would normally be on a retainer. We've made the seats to where they will locate tighter on the bottom and fit the step for the inner spring to give it the correct seat pressure. And to give it the correct rate and everything, just as it were. So we've got a specific retainer and seat now, and what that does is takes the mass away from the retainer and moves the mass to the bottom where it's not in motion. And by doing so, in titanium, we've cut probably a 1/2 gram to 3/4 of a gram off the lightest competitor's retainer. And in steel, it's probably about around 1 gram lighter than the lightest competitor's retainer.
So it's that rotating, it's like getting a set of lightweight wheels or brakes or something like that. It's the rotating mass that you're cutting down on in a way.
Exactly. You're taking that mass in motion away from the valve train.
Will we be offering these in titanium and steel?
We will.
Any price difference?
Nope, they're going to be the same price that we've always done. 100% made here, 100% American materials. Every bit of the manufacturing process is done in North Carolina.
Right on. And so you've designed something a little bit unique to us that's lighter and will perform better.
That's correct.